Topology without points? I mean, that sounds kind of impossible, right? But that's exactly what we're going to dig into, an idea that completely flips our whole understanding of space on its head. Okay, so let's just start with a really big question. I mean, a massive one. What is space fundamentally made of? Like, what are its most basic, indivisible parts? And, the obvious answer, or the one we all probably think of first, is points, right? Space is just this giant, infinite collection of tiny individual points. You can think of them like the fundamental pixels of reality. But what if that's totally backwards? What if points aren't the building blocks we start with, but are actually the final result of some deeper, more complex process? That is the mind-bending idea we are diving into right now. All right, so to really get why this new idea is so radical, we've got to first understand the old way of thinking, the traditional view. Let's just call it the points-first approach. So the fancy name for this is point-set topology. And the key thing here is that you just assume points exist from the get-go. They're just there. The whole concept of space is just a big bag of these pre-existing points. And all the interesting stuff, like shape or what's near what, that all comes from defining the relationships between those points. Okay, to really wrap our heads around this idea of building something fundamental from scratch, let's take a little detour. We're going to step away from geometry for a second and look at something we're all a bit more familiar with: numbers. So think about a number like the square root of 2. We all know it's a real number. It has a place on the number line, but the decimal just goes on and on and on forever, never repeating. So how in the world do you pin down its exact location if you can literally never finish writing it out? Well, here's the really clever part. The trick is you don't start with the square root of 2 itself. You construct it, you trap it. And you do that using things you can define perfectly. Simple fractions, what mathematicians call rational numbers. And here's how that works. First, you start with a pretty wide guess, right? We know it's somewhere between 1 and 2. Then you narrow it down. Okay, it's between 1.4 and 1.5. And you just keep going, getting closer and closer, nesting smaller and smaller intervals inside the last one. If you imagine doing this forever, an infinite sequence of these shrinking boxes, there's only one single location left that's inside all of them. And that location, that is the square root of 2. See, we've defined it not by what it is, but by the process that perfectly corners it. Okay, hold on to that thought, because now we're going to take that exact same logic, that idea of construction by trapping, and bring it right back to space. What if we do the same thing, but instead of trapping a number on a line, we're trapping a location in space? And this is where the mathematician Carl Menger comes in. His work is really the foundation for all this. He basically said, hey, this makes way more sense from a physics point of view. I mean, think about it. We never actually see or measure an infinitely small point, do we? We can only ever observe actual regions, pieces of space. So this is it. This is the core idea of pointless topology. We just throw out the whole assumption that points exist first. Instead, our fundamental building blocks are the things we can actually observe, these finite pieces of space, or, and I love this term, what Menger called lumps. So, if we start with lumps, what's a point? Well, it's just like the square root of 2. A point isn't a thing anymore. It's a process. It's that ideal, perfectly precise location that you define by homing in on it with an infinite, nested sequence of shrinking lumps. It's the destination, not the starting block. But okay, this new definition creates a big problem right away, a huge question. If a point is just a sequence of these lumps, what's to stop us from making, well, bad sequences? Turns out, not just any old sequence of lumps is going to work. Not every sequence will properly zero in on one single unique point. And that was the crucial challenge. To make this whole theory hold up, they needed a really solid, rigorous set of rules, a way to filter out the good sequences that actually make points from all the bad ones that don't. So what does a bad sequence even look like? Well, as Menger pointed out, things can go wrong in a couple of ways. For one, your sequence of lumps might shrink and shrink and shrink and then disappear into nothing, leaving a hole where a point should be. Or it might not shrink enough, and instead of defining a single point, it ends up defining a whole line or maybe even an entire area. Both are no good. And this is where another mathematician, Wald, saved the day. He came up with this brilliant set of logical rules, a criterion, that a sequence of lumps has to follow. You can literally think of it like a quality control checklist. If a sequence of lumps checks all the boxes, boom, it's certified. We call it a point. If it fails the test, well, it's just a bunch of lumps. Okay, so you might be thinking, why go through all this trouble? Is this just some abstract game for mathematicians? And the answer is no way. This, quote, pointless way of thinking actually has some really profound, really important implications. And it's also cool to know that there's more than one way to slice this. The sequence theory we've been talking about, that's like our nested intervals analogy. But there's another approach, a set theory way, that's more like defining a point by the entire collection of all the lumps that contain it. So, a couple of different paths to get to the same powerful idea. So what do we actually gain from all this? What's the big payoff? Well, for one, it connects this super abstract math back to physical reality. Remember, we observe regions, not infinitely small points. It also helps us wrestle with some really deep philosophical problems about what a continuum even is. But maybe the biggest thing is this. It shows that even our most fundamental ideas don't have to be just assumed. They can be built from the ground up. And that really leaves us with one last big thought to chew on. If something as basic, as fundamental as a point can be constructed instead of just assumed, what else are we taking for granted? What other fundamental ideas in science, maybe even in philosophy, are we just accepting as true, when really they're just elegant constructions waiting for us to discover how they're actually built?